Hello everyone, let's go ahead and talk about how we can use improper integrals to compare with other improper integrals to determine whether or not those integrals converge or diverge. There's going to be a very important key fact that we're going to have to investigate in order for us to go ahead and compare improper integrals in order to determine convergence or divergence. And it's this integral right here. It's the improper integral from 1 to infinity of 1 over x to the p d of x. And what we're going to do is we're going to let p be any number that we want it to be. And so notice again, this is going to be an improper integral, so we need to go ahead and change the upper limit to b and take the limit as b approaches infinity of now a well-defined indefinite integral. Now if we go ahead and use our anti-differentiation rules for the power rule, I know that this particular definite integral is going to result in this right here, and my limits of integration are going to be from 1 to b. So for the values of x, I substituted the b and the 1, and notice that what happens then is that I come out with 1 over negative p plus 1 for this here, because again I'm distributing this common scalar to both of these terms here and here, and I have the b to the negative p plus 1 divided by the negative p plus 1. Now what exactly happens to this? How can we go ahead and analyze whether or not that converges or diverges? So in other words, given this particular value, how can I go ahead and determine for different values of p whether or not that converges or diverges? So what I can do then is, well, I can go ahead and take a look at this particular value here, this negative p plus 1, and I can say that that is either going to be positive, negative, or 0. So let's go ahead and say, for example, if this negative p plus 1 was less than 0, in other words it's negative, okay, then what's going to happen then is that this whole thing right here, this exponent is actually going to be a negative exponent, which means then that this particular b raised to that exponent is going to be moved into the denominator as a positive exponent. And being that b is going to be approaching infinity, then b to that positive exponent in the denominator is going to make this go to 0. Because you're going to have a constant over infinity, which means that this is going to go to 0. And of course this has no relationship whatsoever to the limit as b approaches infinity because there's no b there. So what I come out with is just 1 over p minus 1, and therefore it converges. So if I know that negative p plus 1 is less than 0, that's the equivalent thing of saying that p is greater than 1. So if p is greater than 1 for this particular improper integral, we know that the result is going to be a converging improper integral. Now let's go ahead and take a look at when p is equal to 1, in other words when this negative p plus 1 is equal to 0. Well, if that's the case, then we know that this was the integral from 1 to infinity of 1 over x d of x. We change the upper limit of integration to b and take the limit as b approaches infinity. We integrate, and we evaluate, and we know that the limit as b approaches infinity of the natural log of b is just going to be infinity, and therefore it diverges. So when p is equal to 1, this here diverges. Now, we need to go ahead and see what happens when negative p plus 1 is greater than 0, or in other words, this exponent is positive. Now, if we do that, what we're going to come out with is, again, this is going to be a positive exponent here. So infinity raised to a positive exponent, of course, is going to be infinity, minus this here, of course, which is just going to be a constant, and of course we come up with infinity. And therefore we know that it diverges if p is less than 1. So here's the key fact that we need to go ahead and keep in mind, is that if we have any integral from 1 to infinity in the form of 1 over x to the p d of x, if p is greater than 1, then automatically the improper integral is going to converge. You don't even have to evaluate what the integral is going to be. You know it's going to converge. So, for example, if you see anything that looks like the improper integral from 1 to infinity of 1 over x squared d of x, converge. 1 over x to the third, integrated from 1 to infinity d of x, converge. Now, if we go ahead and take a look at values of p that are less than or equal to 1, then we know that the improper integral is going to diverge. And this is, of course, going to be the most counterintuitive one here, is the integral from 1 to infinity of 1 over x d of x. That is going to diverge. And of course, something like the integral from 1 to infinity of 1 over x to the negative 1 d of x is going to diverge as well. And this one should be hopefully very obvious. That's the same thing as the integral from 1 to infinity of x d of x. And of course, that's going to diverge. So, what we needed to do then is we needed to establish this key fact with regards to a very simple looking improper integral, because what we're going to do next is we're going to go ahead and compare these particular simple integrals to other integrals, improper integrals, that are much more complex. But remember, the thing is that we're not necessarily interested in finding out what it converges to. What we are concerned about is whether it converges or diverges. And that's it. That's it. So even when it comes to these kind of situation over here, I'm not interested in knowing what it converges to. We don't need to know that. All we need to know is whether it converges or diverges. Okay? And this key fact here is going to help us to determine whether more complicated improper integrals that cannot be integrated are going to diverge or converge. And we'll take a look at a couple of examples in the next section. See you then.